Okay, thank you for coming back. And let's resume from unsupervised learning. So maybe I'm going too quick this morning and I will try to slow down and also get a little bit thought issue. So if you cannot hear me clearly, so please yelling at me that I need to pronounce larger. So for unsupervised learning, it's not like supervised learning. We don't have the correct labels for training. So remember supervised learning, we have those labels. It's either being manually labeled or it's like generated by our data ourselves, our user ourselves. So for unsupervised learning, for example, we can do some clustering and topic modeling. We have maybe a bunch of query and we want to split or clustering them to different topics. But we don't know for those topics whether it belongs to this topic group or another one. So they're kind of unsupervised learning. Another example is a recommendation algorithm. We're trying to group different customers together according to what books or what movies do they watch, what books do they like. This is a real use case for ML. And that is another clustering example that we're clustering different customers together and do the personalization and recommendation. So I will talk about one interesting unsupervised learning model, which is the K-means. And the reason why it's popular is it's super straightforward. You can say from the left-hand side, you have a bunch of groups, and you want to do maybe clustering them a little bit. You can do maybe straight linear SVM on the left-hand side to be clustered into two groups, or you can choose the cluster to be three, like the right-hand side, where you have this blue, orange, and green. And you have this centroid, which is your choose for your cluster. So what does this algorithm really doing now? What is happening? Okay, so K-mean is a clustering algorithm. What does it do is it iteratively separate data into K clusters. And this K cluster is what you initialize here for. You can initialize K equals to 5 or 10 from your choice. And what you want to do is you want to minimize the sum of distance from each of the centroid to all the examples within that group of clusters. So step 1, you assign each instance to the closed centroids. In step 2, you recompute each of the center from the assigned instance. It doesn't work. I don't. But. So here's the algorithm how to calculate the distance. So now we can use the sum of square laws, which is L2 norm, as you can see on the right-hand side here. And you will sum up all the centroids and all the examples. So the K is the centroid and N are the examples. And we call it SSE, which is sum of square norm. And you can see from the left-hand side, we have this elbow-shaped curve. And you can see on the x-axis will be the number of cluster, which is the K, from 1 to 10. And then from the h-axis, the y-axis, it's SSE, the sum of squared arrow. And when you have only one cluster, definitely you have the longest distance, each data from the longest distance from its centroid. And if you currently add K and increase it a little bit larger, the SSE will drop definitely much more. And some people always ask, how do you choose the right K? So a state of art or a general application is that you choose the point on your elbow. And this one, you have the highest slope before that and a little bit lower slope after that. So as you can see, definitely more cluster implies a smaller SSE because you're trying to add centroids and those points are close to it. So the advantages for K-mean algorithm it will definitely guarantee to converge to some local minimum. Probably it won't converge to global, but definitely guarantee for local. And the disadvantages is that it also suffers from the curse of dimensionalities. And the user need to determine or provide the number of clusters that you want. So for this case, even though we know that this elbow point is whatever we want, but we need to run this several times until maybe to a large k number to find this optimal k. So any questions? Yeah. Yeah, good question. So k-nearest neighbor first difference is like it's a classification algorithm, so it's supervised learning, but this is unsupervised learning. So for k-nearest neighbors, you will definitely set up know what is like the k-nearest neighbor you want to try. You know what is the class it will belongs to, and you have these class labels, and you use that to classify the new labels. But this k means is like you can assign random k, so it will be any class. Like it can be 100 million if you have enough data. Good question. Anything? Yeah. In the far back, please.
What is cluster? What is cluster? Cluster. What is it?
Oh, what is cluster?
Yes.
Oh, so cluster you can think about as a class. So for example, for a topic model, you will split your dataset to different topics, and each topic is a class, and we also call it a cluster. So you can think of a group of data that have the same functionalities or characteristics, and you will group them together to be a class. Yeah. Okay, so the question, I will repeat it, is that if we have this elbow curve, not like an elbow, it's like, I don't know how to say it's a smooth elbow. So how do we decide it? That's a really good question. I never made this kind of a situation before. But I guess what you want is like you have the highest, maybe like the optimum slope that you want to try to do. But it definitely won't be that smooth because it's one data point. It's like all the integer there is not continuous, right? So you will definitely find some not that smooth curves. So someone which have like a highest slope dropped, probably you will choose that optimal point. Yes. Good question. Yep. The curse of dimensionalities. Yes. Let me go back. Where do I say it? Yeah. Okay. So the question is why is suffering from curse of dimensionalities? Let me think a little bit. I guess the reason is the same. So curse of dimensionality is like the much more feature you have, and your training time, training the complexity will grow exponentially. So think about this way. So now you have this number of features, and you trying to classify using maybe, for example, 5 clusters, and you want to figure out what is like the optimal case for this, and then you add more features, and then you will need to scroll to like the same function, calculate the same SSE one more times for this case again, and then using like different, like using this I, W, and this W will be like much larger, right, compared with previously. And you see like this is 2 double sum together, so it will be n squared. So that's why your complexity will explode. Yeah. Any other question? Okay. So this is a pretty useful picture. I don't know whether anyone said it before. It's generated by scikit-learn, which is a famous machine learning package that people use. We also call it scikit-learn. And it kind of summarizes all the different algorithms. So for example, we have this classification. I introduced like this kernel function where you introduce a k-neighbors, linear 3C, and also I'm going to introduce SGD a little bit later for neural network. And this is worked if your training dataset is smaller than 100K. And what about your training dataset is, sorry, my bad. So this is also work for this smaller than 10K dataset. And you can do the clustering, for example, using the k-means. And there are also any other famous clustering examples for unsupervised learning. But I don't use them quite often, so probably it's not the good person to introduce it. But you can definitely look online to see whether they're useful for your specific case. Also, here's funny. You have this sample if it's smaller than 15, probably need to click the dataset. And if it's bigger, you can go to the next loop and produce a quantity, come to the regression or classification. And you can also do some dimension reduction using PCA or other SGD algorithm. I will introduce that a little bit later tomorrow. And so next, after unsupervised learning, I'm going to talk a little bit of reinforcement learning since it's quite important and popular. So for reinforcement learning, it's our agent that tries to learn by interacting with the environment and observing the result during these interactions. So some famous example like AlphaGo and AlphaGo Zero, which are trained on themselves just by playing by themselves. And also a lot of robotics algorithms use deep reinforcement learning. By the way, there's like if you're really interested into deep reinforcement learning, there's a really great course that I just took from UC Berkeley. It's taught by Sergey Levin. I believe he's still talking about for the next fall. So if you're interested, reach to me. I can introduce you to that course. It's pretty valuable for you to learn. And I will going to talk about the machine learning workflows for the next few, maybe 30 minutes or 1 hour. And so what is the machine learning workflow? It will be super useful no matter whether you're doing research or you're trying to put some model in production. So what it does is like you have the label and the raw data, and you put them, split them into the training dataset, sometimes the dev dataset and test dataset, and then you processing it, or maybe data cleaning a little bit and doing some feature extraction, normalization, and doing some feature selection, and do some PCA dimensional reductions, or you're sampling for those ensemble method. And after this, like pre-processing, you go to the next step for the training and learning, and that's how your like the previous machine learning method or deep learning method coming into, and you will do a lot of bit, maybe model comparison from, for example, SVM to a linear model or to the neural network, and you will do maybe cross validation if your dataset is not that large enough, and you probably want to have some performance metric to compare different models and tune the hyperparameters. And after you're super comfortable with your current models that you choose, and then you will jump to the final model evaluation, which will be evaluated on the test dataset. So you have this new model come in, and you are coming back the loop to the test dataset here, and to say whether your model is legit enough. If it's not, then you will go back to the loop, come back to pre-processing, maybe add more features, maybe do more data augmentations, and trying to get a new model and go back to this loop. And until you are super comfortable with your models, then you can go to the final step, which is the prediction, and which is like you can put your model into production, and for the new data, it predicts the new label. And so this is a whole machine learning workflow and why it's important. And there's like offline learning for the first three squares here. And then if you train a model on the first three squares, and then you put the model, release it, put it on the AWS server, whatever server, and when the new data come in, you predict. It calls like offline learning. And for the online learning, which most of the big tech company like Facebook, like Amazon, is happening now, it's like they try to train their model every day to update all the parameters because there are just so many data, and the people's bias might change, people's performance might change based on the current news, based on the weather, I don't know. So based on the new data, they're trying to adjust their models every day, and that's called online learning. And so I will going to introduce each of the steps one by one in details. And we're going to start from the problem formulation and to data processing, feature engineering, training and learning. Yeah. Yeah, I can repeat it. No worries.
Yeah, you mentioned that Amazon train the data every day. So because it's grows so much, so what's the growth percentage that you think that you should consider to do it? Because normally, if the data is not that much, I usually do training like once a month or something like that. But this is the first case that I heard that is every day.
Yeah. That's a really good question. That's only happening, I believe, if you have billions of data. Like I only know that Facebook and Amazon. I don't know any other companies doing that. I believe Uber is doing that monthly. That's just like about a year ago when I heard about that talk from an Uber director, but I don't know what's happening now. But the reason is that because the data is just currently updated with the new features, like new data come in, even though the previously outliers that we removed might be a normal data now. So that's why they kind of keep updating and retrain again. And I don't think any other company needs to retrain every day for now because they don't have that scale, that much quantity of data. And it's also you need a huge pipeline, huge bunch of engineers to build the pipeline to retrain every day. You need so much power to retrain it. So that will be a huge, large amount of work for maybe any other company. They don't have that infrastructure yet.
And you mentioned that in terms of the amount of data is like billion, right? But in terms of the growth, what is that the billion, the growth like
the
what's
growth
the percentage?
Of data.
Yeah, the percentage of the growth. Let's say like yesterday you have like 100, and today you have like 50% growth, like 150. So is that the point that you should consider doing every day, like doing the training every day? Because I feel like it's more like about the growth more than just the number of the
so
data
you mean
itself.
the update frequency should be kind of relative to
the growth, and that's my
the data growth.
hypothesis.
Yes, that makes sense. That definitely makes sense. But think out that when you train a model, it should be already have some amount of data. And for example, for Ubers, they have like their rides every day. Uber is like the Grab here, which is like taxi and share company, and their data is like kind of grow, but they still train monthly. So think about why is that? Even though I don't know what kind of transaction do they have, but it could be millions. But the growth rate might be high because Uber is trying to expand it to the worldwide. But I didn't say that happen even though they're trying to retrain it. If the new model doesn't change that much compared with the previous model, there's no reason to retrain it and replace it, right?
Okay, so you're probably saying that first Amazon, maybe you foresee some benefit from training every day, like the insights maybe change.
Definitely. Because the thing for Amazon is like we need to capture the user preference. Like maybe some product just recently got popular, so we won't need to recommend the user with relevant product. Yeah, and there are also some like seasonalities, or for example, the Prime Day. I don't know whether you guys buy something on Prime Day, so we definitely need to prepare for that model.
I see. Got it. Thank you so much.
No problem. And that's a good question. Any other question before I start? Okay, so I will start one by one for the following steps. And the first part is a problem formulation. So before you start doing the machine learning, and the first thing you need to try is whether it's a machine learning problem. So you need to understand what's the problem to be solved. If it's a too big machine learning problem, do you need to disassemble it to different small pieces and solve it one by one, maybe for different team? For example, for the autonomous drivings, you have the CV team to do all the image recognition or object direct, another team doing the object detection, another team like just say what is the weather, whether we need to care about the sweep. So different functionalities for the huge problem. And the third thing is, as what I just said, is whether the machine learning is appropriate approach here. Maybe there's some rule-based or standard coding if-else problem, we can just solve it. For example, if I'm coming the MLRS for the talk, should I just go by plane or go by car, go by ship? So it's like an if-else problem. The machine learning should not tell me something, right? And on the other hand, if this problem is too hard, probably the patterns cannot capture it, and that's why we are considering machine learning or deep learning. And next question is, what data are available now? So if it's a large data set, as you can see from the scikit-learn chart, if it's smaller than 50, probably you need to go back to collect more data. And even if you have enough data, you probably still need to consider whether you have covariance shift. So probably you are trying to classify the cat or dog for special species of them, and you are training only on special species of such dog, and you're trying to classify another species of the dogs. So probably you won't find a really interesting model to do it, because this is called covariance shift, that the training data set and the testing data set has like has like their features super different with each other. And after you are making sure that you have enough data and this data are kind of generalized to train models, the next thing you need to understand is what type of machine learning problem is it? Whether it's a classification problem, it's a regression problem, can we do unsupervised learning on that? And just like think out of the box to say what it can be happen there. And last but not least, the evaluation matrix is also important here to measure a qualified model. As just the audience said, that we need how often should we update your new models? So you need to have maybe a bunch of matrices that list together, and you measure it one by one. If you see a huge improvement, then probably you can replace it. And that's how you measure the model's qualities, which should be predefined before you start training your models. And the second step is data preprocessing. So I'd like to talk about funny story from CES, which this year is Consumer Electronic Conference, which is the biggest conference, and lots of big or smaller tech companies are coming there to show their muscle, like show their newest product. So I know that Uber is coming there to showing their flying cars, and Sony is coming there to showing their huge TV, which are like 4D display, pretty fancy. And so there's startups there that they are doing some smart rendering machine demo that are trying to identify the purchase just with your camera. I don't know whether you guys heard of Amazon Go, which you just walk into the Amazon Go shop and you scan your code using your phone, and you walk in. It's like it's a grocery store, and you can grab anything you want. And there are some camera just watch you, and you don't need to show anyone your credit card. The camera will just know your face, and they know what you grab. You just grab that, put it in your pocket, and just go. And we tried a bunch of times. We have like our coworker and me. We just like come out to that door together, like holding that at the same time. And sometimes I grab that and pass to him, and he pass to another guy. And we try to do a lot of it, but they're really good at it. Like they're probably different angles of a camera trying to catch our, which is kind of sneaky. But that's it. And what they're doing, sorry, let's go back to the topic. Like the demo at CES, it failed. So the reason why it failed, they're like different light temperature compared with their training data. And also maybe the demo table is like too shiny. There is like reflection there for those objects, and the camera cannot compare the reflection with the real object. So it failed. And what is the fix? Luckily, they fixed the second day, which is pretty good. What do? They collect the new data from the first day, which are all those like different light temperature and the shiny photos. And also they buy a tablecloth. They put on the table and there's no reflection there. And then they retrain all night and the new model is coming, which works. Pretty smart. So that's bring us to the data quality part. So we have a lot of questions with the data. That's why the data scientists nowadays always spend 90% of their time, really 90% of their time cleaning the data. So we always so previously I also been a data scientist for a year. I always call myself data cleaner. It's like stay with the data, like cleaning. So what should we do? There are like missing data problem, imbalanced data, noisy data, messy data. So this messy data can be specifically for the NLP problem that I used to deal with a lot. You will see like, I used to deal with like survey data, so people complain about something. So they have this misspell about the name, so I don't know who they're complaining to. And they have the duplicate names, but they also have the punctuation with like the angry face. They also have like special characters from different language, and they also have this formatting errors, etc. And besides NLP, we also have data on different scales. You probably need to rescale it and normalize it. And we also have multi-type of data. Yep, any question? Oh. Maybe it will take some time, but I will still talking. Okay, that's good. So we may also have the mixed type of data. Say if you're trying to predict a housing price, and you have this data that this in this school zone and with another school zone, and you probably need to compare the school zone's name or compare the school zone's like teachers, etc. So you probably have the crime rate. You probably will know whether it's a safe, whether there's a gunshot there. So like different type of data, and you will also have some sample bias when you collect the data. Like the previous case, the sample bias is that they don't have really last data for those relaxation pictures, and they don't have the good light temperature. And sometimes when you do like a regression model, you probably need to deal with the highly correlated features, etc., etc. There are so many problems that you need to deal with for the data. So, what can you do for the data processing? So first, if it's like some variable, the categorical variable, you can using one-hot encoding. So what you do is like, for example, you have this 10 class, and it will encode one of them through one-hot encoding to 10 element vectors, and each vectors will have one for that specific row, and have 0 for any other element. So which is called one-hot encoding. And second is how you handling the missing value. This happening a lot. So you probably have two cases to try. The first, you can drop it, but be sure don't drop too much features. sometimes even you originally have 100 features, and if you set a bar like if this just has a meaning 50% and you will drop it, then probably in the end you will only have like 5 or 6 features left, which are not that useful. Or you can also choose to fill it, and then you need to decide whether you need to fill it using the average, the mean, or maybe if it's a classification example, you will choose the most frequent vote, the majority vote. The third is data cleaning. You probably need to clean some outliers if you are doing the time series. For example, if you're doing the fraud detections, be sure that you don't remove those outliers for that fraud. Maybe there's a features. So make sure that when something you need to remove, something you do not remove. If it's like you're doing a regression problem using a house price that are give you a super weird loss, and it will maybe take 10% or 20% of the total loss, then probably it will be outlier for you to remove for this model. But later, if you collect more data, probably it won't be outliers. It's just like the covariance shift, or maybe it's more generalized. And for NLP, what you can do, you do a lot of grammar correction, a different sentence correction, and also you can do stemming, limit heading, and also tokenizations, etc. And what else? So now you have this data set. Probably it's not large enough. And what you can do is you do the data augmentation for different field. For NLP, you can do the translation. So if you're training on an English model, you can translate it to, for example, Thai language, and then you translate back to English language, then they will probably return you a different word but has a similar semantic meaning. And you can use that with a label to train your models. And think about that, it will be exponentially grows. So if you transfer one sentence to maybe return you 2 similar sentences in the Thai language, and then if you also choose 2 transfer back, then your data will double 4 times, right? So it will exponentially grows. And similarly for the speech, you can also add some background noise, maybe change the speed of the videos or radios for the speech, and to do the data augmentation. And also for computer vision, you can do a lot more funny things I will show you later. So the first thing you can do is flip. So you have this cat. You can flip it vertically, horizontally, and we can still recognize it's a cat, right? What else we can do? We can crop it. We crop it head, crop it cross, and with some random aspect of ratios, and select maybe random area of size, and choose a random position to crop it. So it will be different part of cat, but maybe the first and second one is not that cat. Maybe it's a tiger, but we can still say it's a cat, right? And you can take it to different colors of cat. So you can do the scale of hue, of saturation, of brightness, or play with the numbers, like you play with the photo apps. So you will have the blue cat, you have the green cat, different color of cat with brightness and hue. And that should be the data augmentation. That's what you can do. You can add noise in the middle of the photos, even though it's not that clear anymore, but it's still right? It's not a cat. So what we do this original. I have the original data set. It's the original cat. We crop it, we flip it, we horizontally turn it. We add hue, we add brightness to this augmented data set. You can see it's like 12 times compared with original ones. And then you fit it in your models, and you hope it still be a cat. So before that, anyone has questions? Yeah.
You mentioned that even you are a scientist, but you spend most of your time to clean data.
Exactly.
Right. So I wonder, is there any special job position in your company that can help you to do this data cleaning, or is it all the job responsibility for data scientists?
Well, that's a really good question. So I don't know what's happening in the Asia area, but in the United States or the North American area, the job function for data science is vary a lot within different company. For example, for data scientists in Facebook, most of them write SQL query. They don't really do machine learning, so they just do SQL query or query different feature because Facebook has a huge data set. You cannot train that using Python; it's too slow. And that's why they write SQL query. They query them out, and they will take it out and put it to the machine learning engineers, and they will train the models. So probably data science and Facebook, they're kind of data cleaning or data extraction, data mining, data miner. But in different, I'm not quite sure about Amazon's data scientist because I just joined Amazon recently for about a month. I'm not quite sure what different functionality do they have, but I know that from my previous job, I'm kind of at a startup and there are only like 5 or 6 data scientists there. So I have to do everything from the startup from scratch to in the end on the production. So everything together, but why can't? How much time do I really process and clean the data? I spend a lot. Yeah. So there's no that special functions for people. Maybe you can hire a third party that they will maybe label it a bit for you and clean a little bit for you. But I feel like for the current trend, I still see a lot of data scientists spend lots of time cleaning. Yeah.
I have a question.
Yeah.
Too. I've seen in the data set that you have some part of the cat, like partial cat,
Oh, yeah.
a picture of partial cat. So I'm just curious, how important that we have to include some of, partial of the pictures, because like at first I was thinking that it might be adding some noise to the model instead of like adding value, because this from this picture alone could confuse the picture that hey, this maybe like tiger or something like that.
Yes.
Just curious.
Yeah, exactly. So the reason for us to do the data argumentation is because our current assets is too small and it's lack of generalizations. So you're right. If you crop this, it might be a tiger. But think about that. If my classification example is either it's either cat, dogs, or rat. So we only have 3 cats and they're totally different. And maybe cropping that will help you a lot. But if you're doing the ImageNet classification, you have 1,000 class there, then probably it's not a good idea. But at that case, they already have a lot of data. So even though you do the data augmentation, you probably don't need to crop to that smaller size. Yeah. And another case is that, so here we only do the object detection for one object. But later, I can show you something. We can do object detection over the whole picture. So, for example, if I say this classroom as a photos, we have a bunch of people. Everyone is like a square of like people with a confidence of 99%, and then we can classify the light. We can also classify the camera back then. So it's different object detections. So at that point, maybe cropping won't be that helpful.
Thank you.
Yeah, no problem. I believe there is a question back then. Yeah.
Actually, I have 2 questions.
Okay, great.
Yeah, first is about the correlation. You were talking about we are having a class and we can just predict as a one variable. So, for example, if I want to predict 2 variables, for example, maybe I want for example, the cast is clear and then the player can play. So so if they are going to play, decision is going to be made. There is a weather, a data set over there to test whether to predict if you can play or not. So the decision is based on if the weather is clear, then the player can go for the play. So play yes or no are two labels for that class. But then if we are testing that data set, we just predicting one, instance. If we one attribute. But if we want to predict multiple, so how would we do that? For example, based on that, if that person is going to play, then I want to make another prediction how much maybe some incentive he is going to get. So I want to make two prediction. So how could be that possible? I was checking on this. And the second question, you just could you please answer it? Then I would just rephrase my second question.
Sure. So if I'm understanding correctly, you're asking that what's the difference between binary classification or multi-class classification? Is that your question?
No, I'm not asking that one. Usually, only predictor or maybe independent variables could be the many one, but we just predict one attribute. So if we want to do multiple predictions, how could we do?
I see. That's a good question. So you mean that the output might have some relevant with each other? I don't know whether there's some model will help each other to predict. Probably when you go to deep learning, the GAN models will help, which generate adversarial models. But for your case, I would say you can always train two models and see whether the correlations or some causations happening there within these two models. So I don't have a great user case for you. Sorry.
Yeah, maybe we should have two different models and two different one and then combine that one. Probably this could be the solution I was testing. By taking just two test cases differently and then combining it later into one application app.
Yeah. If you can do this two model parallelized, that definitely be great case. But if it's kind of sequential model that one result is heavily relies on the other, which there's some causation issue, then probably you need to train it first and get this label and get another more features, train the second models. So I would say it will be different use case. It's really kind of hard to say, but that's a good question.
Thank you.
Great. Yeah.
If you have a problem but you have no data, what is the criteria for choosing the data for solve this problem?
So the question is, if we have no data for a machine learning problem? Wow, that's super hard. Several ideas. First, come back to the first part, whether it can be solved by machine learning problem. So for example, you're building your own website. Maybe it's like a Facebook, but you don't have users' preference data. Or maybe you're building online shopping. You don't have that much data as Amazon. So you can borrow and steal. There's a lot of online data set that you can steal. So Amazon's data is definitely not publicly online, but you can steal a lot of similar data with similar features that you can borrow still, right? But be sure that it's legal first. And be sure there's not covariance shift, so which means that your product's features, like you're trying to sell laptop and the other online data set is trying to sell phone. And probably there's some feature difference you need to take care of and do some feature engineering yourself. But definitely look on something online, it's a good start point. Okay, great. That's a pretty funny question. Any more questions?
Sorry, I have another question. You were just a minute, couple of minutes. You were sharing that you people do lots of cleansing process. May I know? Do you use some tools or maybe crowdsourcing services with Amazon, or it's the manual one? What kind of? I mean, how would you do? Could you technically?
Okay, good question. So to be clear, now I'm not a data scientist at Amazon, so I don't know what the data science really do. So what we are doing is like really building some deep learning models ourselves, so we don't really touch a lot about the data. But I have some experience from my previous job as a data scientist, and we are kind of NLP company trying to apply an analysis on the user's survey data, which is super noisy and so many grammar errors. It's like unstructured data. We need to a lot of stemming and lemmatizing. So there is like NLP package called NLTK. I believe someone here must hear of it. It's super useful for you to clean in. And also if you use a little bit established package, there's a package called Spacy, SPACY. So it's also pretty useful, and you can download this English tokenization dictionary, and it can help me automatically stemming it, lemmatizing it, maybe correct the grammar issues a little bit, remove the punctuation, do the tokenizing, etc. So this will be the useful packages I will recommend you. Yeah, no problem.
I have the question about sparse data set. Sparse data set, do we need, is it coming into the category of, is it qualifying for the feature reductions, for the better efficiency? Because, and the other one is that, can we categorize it into the normalization process? So where does it falls?
Yeah, that's a good question. So question is like the sparse data set, and you mean the features are the sparse, right? The target values?
Data values.
Okay, so you mean the class are really unbalanced.
Yeah, maybe. I mean, many features are having zero values. Just in a one attribute, just one or two, three ones are there, just like that.
I see. So you mean you have the sparse features for just several features?
Yeah.
So let's come back to our previous data augmentation thing that we're trying to talk about. That how do you fill it? Whether you should fill it or whether you should drop it. I don't know where is it. But for some of the case, I would say those tree method is super helpful for the sparse data set. And of course, if you do a neural network, probably you don't need to drop too much. But if you do traditional machine learning models that I just showed you guys in this morning, probably need to care this about how to fill the data set. If you want to fill with me, if you only have like maybe 1% of that for that features that include those data, probably you will drop it. It won't be that useful, but it also depends. So I would suggest you to train on different models, to train on traditional machine learning models and then a train models, and to compare like random forest or XGBoost to see that whether you will see a big performance to jump, a boost, even though you didn't remove that sparse features. Yeah. Good question. Yeah.
I have a question about supervised learning models. What can we do if someone might accidentally put the wrong label into the data?
That's a good question. I have this issue a lot. So previously, we put our training data set and on the Amazon Mechanical Turk. And so there's someone, like, I don't know where they are. They will just label it for us. And a lot of them are not that reliable. So we have a lot of wrong labels. So what do? We have like 5 different workers to label one thing, and we'll choose the majority vote if like at least four of them agree with each other, we'll use that as a training data set. If no, then we'll just drop it. So which costs us a lot of time to relabel it ourselves. But on the other hand, a little bit, not that too much, wrong labels will also help us to inject some noise. So it's not only the basic.
What if that label have been trained into your model? Can you untrain it?
Can I retrain it?
Yeah,
Or-
like for example, if I have a picture of a dog and I train it as a cat, so it has been trained into my model. Can I fix?
Yeah, of course. Yeah, so since the model, that's why I talk about like the data cleaning is like spend most of the time when I train the models. Because when you train the model, you already have the architectures, you have everything, hyperparameter set in there. So what you need to do is just fit in your existing like qualified data set in. So if you have those wrong label, you go back, correct it, and retrain it. If it's not like the BERT or like those data of like neural network models that will take you a lot of time to train, then you're always good to correct the label and retrain.
So you're saying I have to go to find that earlier picture or data, right? And recollect it.
Yeah. So that comes to when you evaluate the models. So you will try to do some classification to say why this model make this predictions wrong. So probably it's because first your label is wrong, or maybe it's because some of the model you choose is wrong. So there are different of criteria to desymbolize your wrong labeling or wrong prediction. So kind of you can know what to improve.
Thank you.
No problem. Yeah. That's a good question. So the question is that whether there exists like information leaks from label to features. So you mean now so previously we have this py given x, and now it's relative to the px given y. That's a good question. I need to think about it. I haven't made that before, but that definitely exists a lot in the real world. I would say go back to those features and trying to isolate them and see what will happen to your new models. So if it's helped, because in the real world case, we always say these features and new labels have some interaction with each other, dependence with each other. We cannot have some like correlation equals to 0. So the information leaks happens all the time, I would say. Probably you can do is do some dimension reduction, or like to extract some principal component element. Or you can, that's really hard to be honest, and you can check whether some of the feature really can be predicted by your labels. Yeah, but I don't have a really good answer for that question. Okay, great. Let's continue. After this cut, we can go feature engineering. So after you think your dataset is legit and you're ready to go, so you probably can do some feature engineering here. You can use your existing domain knowledge. For example, for NLP, we also hire lots of linguistics with us, and I learned about during my internship there as a data scientist with those linguistics to know this language structures, and you can use that to create the normal feature. Similarly, I know those healthcare company when they're trying to build new models, they also hire a lot of not only engineer but also pharmacists to help them like label data and using their prior domain knowledge. And you can also normalize the data using the mean variance. Mean and standard deviation. So why we need to normalize it? think about, again, the housing pricing, or for example, like the stock price predicting. So you have different kind of features within on different scales. So probably you have some feature within minus a million to a million, and then you have some feature with only like 1 and 0. So you have their weights, which are super like L-defined, and it will be influenced a lot if you have the data issue. And that's why you need to scale it, normalize it, and it's pretty important use case for deep learning. So we call it batch normalization. I will talk about it a bit later, but pretty important to normalize a feature before the next step. And another rescaling method is minimax rescaling, that you use the xi minus the x mini value and divide it by the x max minus the x min, which you will kind of have this range between 0 and 1. And some rule of thumb here: when you do feature engineering, don't overthink too much. Don't think that your prior knowledge will predict the housing price. Probably it's just your bias. It won't work sometimes. Just something keep in mind. And next thing is the training. So the most important for the training is that when you evaluate your model, be sure to decide whether it's overfitting or it's underfitting. So here's good photos in the 2-dimensional features, that whether a model is overfitting or underfitting. So on your left-hand side, the model is definitely underfitting, and we also call this model is high biased. So you will see that it only a straight line, and it have a huge loss if you using the L2 norm. And on the right-hand side, it definitely overfitting, since you have those super curly lines that you're trying to split the features. Maybe sometimes one of the features are outliers and your model was wrong. And that happens a lot in the tree case when you classify the models. And we also call overfitting with high variance. And the model in the middle will be good, so it's not overfitting or underfitting. So keep in mind that your error will roughly equals to bias plus variance. So don't be too high bias or don't be too high variance. Or you will have this curve, which is like the bell curve, that will be high bias or high variance. Okay. So why not underfitting or overfitting? So first, for underfitting, is that it is failure to capture some important pattern. It's like maybe you have a lot of useful feature, but your model is too simple. You only have like maybe weights equals to not 0 for 2 features and 0 for any other features, which means you're underfitting here. And that's definitely not that useful. And the second, the model is too simple and it's slick to explain it, and it's not that flexible to generalize to the new data set. And how about overfit? So for overfitting, it also failed to generalize, because for your current data set, you have this too many curly line here. And if you have new data come in, maybe you have this like plus on the right hand side sometimes. Maybe it's on the road here, and it will be super hard for your model to generalize. And secondly, maybe if you're overfitting, maybe you have too many parameters or too high orders, and that means your model is too complex. And sometimes it just means that your model is just memorizes the data. It doesn't really learn some generalization rules. It's corresponding to high variance, so which means that the small change in the training dataset will result a big change in the result. Like think about the train models. If you just change one of the features and the model is overfitting, then probably the weight will suddenly change. Like the tree split node will suddenly change randomly, and then it will be a huge change in the end. And so now you think you're good with the training, and you probably will do some model evaluation. So here are some pretty interesting metrics for you to do the model evaluation. So the first one for the classification model evaluation is a confusion matrix. So it's also the similar diagram that I showed you before. You have the actual class, positive and negative. You have the predicted class, and you have the TP, which is true positive, and you have the false negative, false positive, and TN, which are the true negative. So the TP and TN are your correct label data, and you can calculate the accuracy on your right-hand side. So it will equals to all the data, data in the training set, all the examples are labeling correct, divided by the total number of examples. Pretty straightforward. But the issue here is that sometimes you might have a such unbalanced data that the negative class take a lot of times. Maybe 99% belongs to the negative class and only 1% are positive class. So what should you do? And this happens a lot to us when we do the sentiment analysis and sentiment classification. Sometimes like maybe some class like angry or maybe happy is like pretty common. But some other time when you are really, I don't know, like very sad or you're kind of confused, and this kind of like this ambitious class, and then when we have like maybe 5% of the data, so probably what you can do is do the data argumentation for that class only. So you just do the argumentation for the positive class and try to generate 10 times of more training examples and all label them as one and go back to your training set. It probably will be 50-50 or even like maybe 30-70 will be fine. And several useful metrics besides accuracy. You can test just the positive data's prediction, which is useful for those unbalanced data set. So you can have this precision definition, which equals to TP divided by TP plus FP. So TP plus FP is a total positive data set from your prediction. And I want to know for all the data that you predict using your model, how much of them are really true positive, so which is your precision. And this is pretty common used. Another thing is recall, which equals to the TP divided by the TP plus F1. So this means that for all of the data should be positive, which is the first row here, the actual positive, and how much of them you predict are positive. So which means how much of the positive class can you capture using your models. Pretty important too. And if you want to use both, so this is a kind of diagram showing that on the precision and recall, especially the lower red case will be important. The small green circle and the green square. And if you want to use both of the precision and recall, so you probably can take the harmonic means of them, and you can capture both how generalized your model is and how sensitivity your model is. And for the next case, when you do the training and testing, you can split training and testing data set using like 18% of training and 20% of them to be testing data set. And but if you want to test within the training circle, for example, if you are trying to compare different models with each other, so for one specific class of model training, you probably need this validation data set. So you can split your data set to 60% of training set, 20% of validation set, and 20% of test set. So for the validation set, it will just using when you're training and doing the parameter tuning or compare different models, and you isolate the test data set out and to avoid the data leak to the training or validation data set at the final model testing. And another useful technique is called k-fold cross-validation. So think of that you have a really small data set, and it's really hard for you to just split with training and testing data. So what you can do, you can randomly split them into k-folds of data, and on each of the run, you keep one fold out of it, and you train on the other k-1 fold using these models, and then you test it on the test data set. You get accuracy result, and then you do that for each of the k-fold for the testing data set, and you do k times, and then you average the matrix score to say what is the total performance, which is pretty useful in the traditional statistical knowledge modeling. And some tips for choosing the case. If you choose a case to be too large, definitely it will take more time to train. And if you choose a k too small, for example, you just choose the k to be 2, then there's no difference to split to the train and test data set. And we usually choose k to be like around 5 to 10. And so here's a specific diagram. Okay. So here's a specific diagram for how you do the k-fold validation. So you can see here for the first iteration, you choose a test fold. Second, you change it a little bit, and until the k equals to 10 for the 10th iteration. And then for each iteration, you have this evaluation matrix scores, and now you get the mean score of all of them. And for regression, we also have some evaluation metrics. The pretty useful thing is definitely the L2 norm, which also the Euclidean distance between the prediction and the target. We also call it mean square loss, which is the mean of the two vectors y choose minus the y prediction y hat and the square of them. Yep. For hyperparameter optimization, you mean for each fold I choose a different parameter? So no. For each of the model training, it's fresh, but they should be used a similar one, because if you're choosing different hyperparameter, for example, for the second models, then your model will kind of biased. And so even if you have a higher accuracy, you don't know whether it's because of the data or because of the new hyperparameters you're choosing. So when you're choosing this k-fold, you're keeping the same parameters, same models for all the k-fold. And if you want to change it, you change it and do another run again. Yes. Exactly. So within this k-fold training, for each iteration training for the k-fold, you should fix it like exactly same models for a time. Then you can get the average, which will be a promising scores. Any other question? Yeah. So they'll be different. So the k-fold is pretty useful for the small data set that you want to play with, and you just use k-fold data set. And for validation data set, it's like it can be applied for any other cases that you split to train and test, and then within the hyperparameter tuning for that specific model, you split that to train the validation. So these are like two things. Yeah, so for k-fold, for the k-fold cross-validation, we kind of like test it within, like train it within the current like training data set. It's like different to the previous one, like the validation data set. Do I answer your question?
I mean, I like to know the normal practice if when you apply the k-fold on the training set, right? like after that, do you still need to use any kind of validation set before you
Oh,
really
okay.
apply on the test set?
Okay, then the answer is no. So the K4 validation is kind of specialized validation that just for the smaller data set. But if you have a bigger data set, you can just go ahead and do the validation data set. So you don't need to do each fold one by one. Yeah. Because the K-fold is trying to generate the data within this limit data set, so you want to include everyone in your training, but you can't. So what do? You train every time within each of the model, and you average the score. Yeah. So after L2 loss, another use for metrics for regression is the R-square, which is coefficient of determination. So you can interpret as a fraction of variance accounted by the models, so which is 1 minus MSE divided by the total variance of Y. And this R-square should be between 0 and 1. And you probably, if you're using some scientific package in Python, probably scikit-learn, you will find the R-square B minus is smaller than 0. Theoretically, it should not be happen. This happened because sometimes, like when the computer is trying to memory these figures, it will give you a super smaller minus numbers, and then if you add them up together, it will be smaller. It will be a larger negative value, and then it won't be closer and approximate to 0. So you will see this weird R-square, but don't worry, it's not your problem. And something keep in your mind, when you include more variables or more features in your models, your R-square will always increase. Because a more complex model will always experience more variance. But it doesn't mean that your models is the best one if you include more and more variance with a higher R-squares. Even though the higher R-squares is naturally should be a great model. So what I suggest you to do is probably using the adjust R-square, that you add some penalized term for the number of features that you included in these models. It's called adjust R-square. And last up,